In this lesson, you will learn how to work with imaginary and complex numbers. Imaginary number is defined by the square root of -1. If we take and square each side, we get I squared equals, because squaring and square root cancel one another, I squared is going to equal -1. So it is good to know that I equals the square root of -1, and I squared equals -1. So let's look at some examples to simplify the radicals. Like we've previously learned, we will do prime factorization for the number under the radical. We have the -13. Because we know that I squared equals -1, we'll factor out a -1 using that I squared. So that makes the 13 become positive. Continue to do prime factorization using your prime numbers. 13 is prime. So now we're going to look for our pairs. Well, we have a pair of i's because I squared, that is a pair of i's. And we have no other pairs of like factors. Recall that each thing that you circle gets written outside the radical, and things that are not circled are written inside the radical. So we're going to have our answer I, the square root of 13. Because we had a pair of i's, it gets to go on the outside, and the 13 stays on the inside. Notice you would not write the square root of 13 and then I. We want to make sure that the I is outside the radical, and if you write it after the radical, it may be confused as being inside, and that would not be correct. Let's look now at example number 2. Again, start with prime factorization. -144, when you factor out the I squared, that's factoring out a -1, it makes the -144 becomes positive. We now can continue doing prime factorization. If you actually notice, 144 is a perfect square. So if you know the square root of 144, you wouldn't necessarily have to continue with prime factorization. But we could do prime factors. 2 goes into 144, gives us 72. 2 goes into 72, gives us 36. 2 goes into 36, gives us 18. Another 2 goes into 18, and we get a 9. We actually cannot divide by 2 anymore because it's not even, so we'll have to pick a different prime. We divide by 3, we get 3, and divide by 3, we get a 1. So looking for our pairs, we have a pair of i's, because I squared, that is a pair of i's. We have 2 pairs of 2's and a pair of 3's. So for each thing you circled, that gets written outside of the radical. So we have our I, 2 times 2 times 3. We can simplify that. 2 times 2 times 3 is 12. And of course, our I. In this case, I works a lot like a variable. So you'll put the 12, the coefficient in front, and then the I after that. So again, if you knew the square root of 144, you could have gone straight to the answer 12I. Now knowing that the square root of -1 is I, let's look at example 3. We have -180. So we're going to first factor out the -1 with the I squared, and then continue our prime factorization, dividing by primes. 2 will go into 180 because it's even, gives us 90. We can divide by another 2 because 90 again is even. We get 45. We'll now have to go with a different prime. 45 is divisible by 3. The sum of the digits, 4 plus 5 is 9. If the sum of the digits is divisible by 3, then that number is divisible by 3. We can divide 15 by 3, and then a 5. Now, if you divided by prime numbers in a different order, eventually you would still get these same prime numbers, 2, 2, 3, 3, and a 5. Maybe not necessarily in those order, but it will come out the same. Now look for your pairs. We have a pair of I's, a pair of 2's, a pair of 3's. Notice the 5, we do not have a pair of like factors. So when we write our answer, our I, 2, and 3 get to go outside of the radical, but the 5, it's lonely. It has to stay inside the radical. Let's simplify our answer. 2 times 3 is 6. The I will go after the 6, and then our radical 5. Let's now talk about complex numbers. Complex numbers are in the form a plus bi, where a is our real part and bi is the imaginary part. Let's look at some examples of correct complex numbers. 3 plus 4i, that is a complex number, where 3 is the real part and 4i is the imaginary. We could also do 4 minus 2i. Even though it doesn't have a plus bi term, we really could make it 4 plus a negative 2i, where 4 is the real part and negative 2i is the imaginary. We have 1 minus I square root of 5. Again, this is a complex number written in the correct form, where 1 is the real part and the negative I square root of 5 is the imaginary part. As we previously learned, we would write the I in front of the radical 5 to have correct notation. Now let's look at some non-examples of complex numbers. 4i plus 7i. Those are imaginary plus imaginary. It would need to be a real number and then an imaginary to be complex. So this one is not correct form for a complex number. Also 3i plus 2. That is not in the correct form for a complex number because the real part would need to go first and then the imaginary. So now we're going to find the sum or difference of some complex numbers. We have negative 7 plus 2i that we're going to add with 5 minus 11i. So when you're adding these together, you'll do it very similar like adding polynomials where you combine like terms, where we will add the real numbers, so we'll line them up, the negative 7, line it up with the 5, and we'll add the imaginary numbers, 2 plus the negative 11i, again lining those up. So find the sum. We get negative 2 and negative 9i. So adding these complex numbers works a lot like adding polynomials. Just combine the like terms. Let's look at a subtraction problem. We have the complex number 3 minus 6i. We're going to subtract negative 2 plus 5i. Well, remember that subtraction is the same as adding the opposite. So we're going to keep the first complex number, change subtraction to addition, and change the second complex number to the opposites. So keep, change by adding the opposite. So now we can add these complex numbers. We have 3 minus 6i that we're going to add with 2 minus 5i. Again, lining up the like terms, the real part and the imaginary part of the complex number. We get 5 minus 11i.